junction allowing nature, better isotropy, larger Valiga figure of merit, and higher breakdown field. These properties is better than existing semiconductor materials such as silicon, silicon carbide, gallium nitride. And also this is the crystal structure of alpha gallium oxide, where this is under the rhombohedral phase, or we can we can say hexagonal phase. And next I'm going to discuss about that growth of alpha gallium oxide. How to grow alpha gallium oxide? This is a misuse technique, and this is very promising and very trending, well-known technique, and very easily accessible technique. What is the benefit of this technique? Actually, this is there is a number of techniques we can grow very well, uniform and high quality single crystalline alpha gallium oxide over on sapphire substrate. But misuse among them is different and unique because it's efficient, fairly rapid, cost effective, and low power consumption source vapor growth method. And that already researcher achieved alpha gallium oxide device by misuse techniques, growth technique. So among them, normally of MOSFET, MESFET and Schottky diodes, they achieved, and their breakdown voltage exceed 1 kilovolt and specific low on resistance 0.1 milliohm centimeter square. So in that misuse technique, to grow alpha gallium oxide, the required growth temperature is 400 to 470 degree Celsius. It is a considered lower temperature, and that this misuse there's three units: supply unit, reaction unit, and exhaust unit. So in that supply unit, actually in the precursor solution in that solution container, where bottom of the solution container is placed piezoelectric ultrasonic transducer, which is frequency range is 1.7 to 2.4 megahertz. So this transducer form mist particle from the precursor solution, and then mist particle become carried out with that argon or nitrogen, and then the reaction unit, this carried mist particle then deposited on sapphire substrate in that heating furnace, and then exhaust unit, that pollution section become eliminated. So in that we use sapphire substrate. Why we use? Because after several research among the material, we just realized the sapphire substrate is the lattice constant is very close to this gallium oxide lattice constant. So because for a good crystalline alpha gallium oxide, we need ideal substrate. So sapphire substrate is a very good substrate to deposit alpha gallium oxide. So only 3.5% lattice mismatch between C planes of alpha gallium oxide and sapphire substrate. And also this growth alpha gallium oxide highest achieved electron mobility is 24 centimeter square by voltage second, is very low compared to theoretical value 300. So now I am going to discuss about some achievement in terms of power device and development. So first I am going to talk about the PN heterojunction diode. So this is the alpha iridium oxide and alpha gallium oxide PN heterojunction diode. So here I have we have presented a schematic diagram of this PN junction diode and VI characteristics diagram. So here we can see this is the N plus gallium oxide and N minus gallium oxide, both are thickness is with 0.5 micrometer, and P plus alpha iridium oxide is 1 micrometer. So to form a device, the P and N type p-type n-type layers thickness is very important for better electrical characteristics and better performance. And their n plus and n minus gallium oxide resultant electron concentration is 10 to the power 19 centimeter minus cube, and p plus alpha iridium oxide thickness is 1 micrometer and then whole concentration is 10 to the power 20 centimeter cube. Also sheet resistance 10 to the power 2 ohm by square. So in that case actually the lattice mismatch between iridium oxide and gallium oxide is very small, about 0.3%, which is better than between iridium oxide and C-plane superaccepted, which is 5%. So this both material form a very good heterojunction, and because of due to that perform very well. So, and also in that PN junction device, another part is the contact between metal semiconductor, like ohmic contact. So scientists trying to achieve strong ohmic contact for better carrier concentration, and this will be very helpful for future electronics device, future heterojunction PN heterojunction diode. And in that VI characteristics, that voltage, turn on voltage is 2 volt. So next is coming Schottky barrier diode, alpha gallium oxide Schottky barrier diode. What is Schottky barrier diode? Actually, Schottky barrier diode, when we talk about the junction between metal and semiconductor. So this is like direct contact with metal with semiconductor gallium oxide. So here also like ohmic contact, there are two types of contact, ohmic and Schottky contacts. So I here represent that symmetric structure of Schottky diodes and their VI characteristic. So in 2016, Japan Polspia company first discovered alpha gallium oxide Schottky barrier diode by miscibility technique, and then there is two SBD1 and SBD2. Their thickness is 30 nanometer and 2580 nanometer. Means n minus layer, and n plus layer is 3 to 4 micrometer. So, and they are finding low on resistance is 0.1 and 0.4, as well as high breakdown voltage is 531 and 855 voltage, which is very close to silicon carbide limit. So this result considered is an excellent result, and its performance very well. So for this company, there is undergoing research, and they are trying to decrease the turn on voltage of this by developing the contact metals, and trying to reduce the built-in potential, and finally it will positively impact on device cost. It will reduce the device cost. So the means quality of this Schottky barrier diodes, or attributes of this diode is low switching loss, and due to this low switching loss, having that low resistance and low capacitance in the depletion layer. So now I am just coming to the point, coming to that another section, MOSFETs section. So there is another achievement, this is also same company. In 2016, Polspia and Kyoto University jointly first discovered this PN junction iridium oxide alpha gallium oxide power MOSFET. Already I discussed about PN junction of iridium oxide or alpha gallium oxide. So this is that one diode, and this is MOSFET. So here iridium oxide is a p-type corundum semiconductor, is a function as an inversion layer. What is inversion layer? Actually, in the MOSFET case, there is a p-type MOSFET, n-type MOSFET, and then that classified as a enhancement MOSFET and depletion MOSFET. So this is a enhancement MOSFET, normally off, enhancement MOSFET. Normally off means in that case when voltage is plus positive or negative, then only electron flow, or in the zero voltage no electron flow between the source to gate. So when creation of electric field due to the biasing of uh, gate terminal, so the effect of electric field, one inversion layer channel layer form between the source to gate. So this is the play as an important role. This is like a important role as a carrier of electron flow. So in that case iridium oxide play as an inversion layer. So in that operation section, when we can see the VI characteristics. So when zero voltage there is a no current flow. So when positive voltage, the reduction the depletion width, the depletion layer actually form between the P and N semiconductor, and then when increase the gate bias voltage, uh, the current start to flow from source to drain, and when the threshold voltage 7.9 volt, that time actually current start to flow. So this is VI characteristics, and then there is finding Hall mobility is 2.3 centimeter square by voltage second, and carrier concentration is 1.0 in 10 to the power 21. So this is also quite good achievement over the alpha gallium oxide power device. So another one is indium oxide and alpha gallium oxide MOSFET. So here actually alpha gallium oxide used as a buffer layer. So Canocap first fabricated like indium oxide, which is entitled of 3.3 electron volt band gap, growth on alpha aluminum oxide substrate, and about alpha gallium oxide used as a buffer layer. So what is the importance of buffer layer? Actually it is main work is to reduce the lattice mismatch between the material and substrate. So then as a resultant it will improve the crystal nature at the interface and reduce the defects. So finally it will improve the electrical characteristics. So this the gate length is 8 micrometer and width is 480 micrometer, and this insulator alpha gallium surface substrate thin film is 100 nanometer. So here the resultant drain current on off ratio of drain current is 10 to the power 6, and which is still low, and it's because of these defects in the interface and due to the presence of trap. And the resultant carrier concentration and carrier mobility is 10 to the power 19 and 100. So it is considered good characteristics. And so this is still desirable to reduce the cost of fabricate MOSFET with the high performance. So it seems to raise offset drain current while voltage over 70 voltage, but this was not a deadly breakdown. So still need to improve this indium oxide alpha gallium oxide MOSFET. So next, the final another achievement about alpha gallium oxide MOSFET. This is the normally on depletion mode MOSFET. So what is the difference between MOSFET and MOSFET? In that MOSFET we use the oxide layer, but in that MOSFET there is no oxide layer between the gate and material body. It's a direct contact and metal and semiconductor. So this is like Schottky contact. So in that MOSFET is one of the benefits is it is high switching speed and very good electron mobility. So now we'll see that what is the performance of device when you use gallium oxide as a gallium oxide material. So this is we have taken. This is like a mixed CVD grown ASEAN doped tin doped gallium oxide. So now we'll see electrical characteristics the tin doped gallium oxide on surface substrate. in that normally on depletion mode MOSFET. So here titanium 40 nanometer and gold 40 nanometer ohmic contacts were deposited electron beam evaporation method, and then Schottky AGOX is a Schottky contact deposited by reactive RF sputtering method. And that here actually we have examined, like we have demonstrated two different width to length ratio Schottky diode with their width to length is 260 by 10 and 40 by 5, and their rectification ratio is 9.6 10 to the power 6 and 6.3 10 to the power 6, and barrier height is 1.02 and 0.93. So in that case we just exhibit that net donor concentration in the channel layer means with the depth of channel layer. So in that case we have noticed that the donor concentration is appeared up to the depth of 30 nanometer, and then it's become decline 10 to the power 19 to 10 to the power 18. Means when it's below 30 nanometer, and then higher means this 30 nanometer layer is surface is lower dislocation density. So we can see the non-uniform donor non-uniform distribution of donors in the channel. So that time gate voltage reduced to turn off the FET. So in that in the base of electron concentration we just found out the electron mobility through this certain formula. So also we have seen that in turn on voltage reduce, as well as like electron mobility also reduce, and that is the reason behind that also, that interface quality of this alpha gallium oxide and quality of this material means defect nature of this material. So here the finding this is the VI characteristics, means breakdown characteristics, where we can see that both diode 262 and 10 micrometer both diode in the first case 262 by 10 micrometer MOSFET, when that gate voltage is minus 10 voltage, then drain voltage steadily increase, and when it reach to 48 voltage, then drain current suddenly increase and breakdown occur, and at that time carrier concentration 10 to the power 19. And in that case of 40 by 5 micrometers Schottky diode, that it's increased to minus 19.6, and that time is breakdown occur. So this is the two graph we exhibit the breakdown characteristics. So now I'm just come to the challenges and application section. So in that case, throughout cover up this number of achievement of this alpha gallium oxide device, from the growth to device stage, we observe that there is a three very significant challenges we need to encounter and we have to develop. So in that case, first is doping. So normally for alpha gallium oxide, defect nature is behave as a n-type conductivity. So still now p-type doping is very challenging and is a question in the scientific society, and the requirement of p-type doping is to develop a bipolar p-n junction device. So p-type doping is very important, and the absence of p-type doping is limited the alpha gallium oxide power device capability. So next is thickness. So the most important in the MOSFET or MOSFET power device is like channel layer thickness to evaluate the performance of the device. So we have to control the channel layer thickness, critically control, to also to evaluate, also to control the carrier concentration to better performance, and it will eventually affect device breakdown voltage. So next is defects. Yeah, this is the one of the very important part. The entire device performance depend on the material defects. Means defects means in the growth to device stage, material any kind of cracks or imperfection forms. So which will like location of electron traps. So it will obstacle of flow of electron, and then it will hamper device performance means, such as conduction challenge, transport, threshold voltage, field effect, mobility, and device stability and reliability. So we have to very conscious about, very serious about defects, and we have to reduce the defects of material. And electron mobility is direct relation with drain current as well as Ballica figure of merit. So uh, so in the electric characteristic, in the terms of electron mobility, we have to develop. So apart from this, alpha gallium oxide is a thermally instable, and very poor thermal conductivity is a major obstacle. As well as actually in application stage, alpha gallium oxide mainly used in army sector and also auto vehicle industry, and also large power control in the industry. So in conclusion, we just want to say that gallium oxide is a very demanding wide bandgap semiconductor material for future semiconductor industry. And that review mainly focus on that gallium oxide Schottky barrier diode and FET device. So we from this few number of achievement, we just realize that this device potential still not completely unexplored, but this device significant parameter defined is a very good power device. So there is so many critical challenges we have to overcome, and we have to mm, we have to develop a very good excellent high voltage blocking power device. And here I just summarize that electrical characteristics, status of recent status of electrical characteristics, such as carrier mobility and carrier concentration of power device. This is the enlisted reference, and thank you.